We're just giving people another minute here to join. So start here shortly. Okay, that's 7:01. So, well, my time, 9:01 Eastern. So, welcome everyone to our second webinar. Again, I'm Jeanette. I'm your chair for the competition, and I'm going to introduce here Amiya Maji. He is and I asked your title, you're a senior computational scientist. Did I get that right? At Purdue University, and he's going to be giving our webinar on benchmarking today. So take it away, Amiya.
Awesome. Thank you, Jeanette. All right. Good morning, everyone. I hope that's morning for only the people in the US. Yeah, good afternoon, good evening for everywhere else in the world. Yeah, glad to see so many people trickling in. All right. So today I'm going to give you a high-level overview of all the benchmarking applications that we are going to use this year for the student cluster competition. Okay. And we are not going to go too much into the submission instructions or grading in this particular webinar. So we will, once we post those details into the website, we will have pretty detailed instructions of how you can submit your results, what we are looking for, how those would be graded, and so on. Okay, so today is more about just a high-level overview of various benchmarks, and then I'll be giving you a few resources for you guys to try out, point you to different tuning guides that I have found online and so on. So just to help you along your way. Okay. All right, let me see if I can share my screen first. Can everyone see my screen?
Yep, that looks good, Amiya.
Okay, good. All right, so slideshow. All right, everyone see my slides? Good.
Yep, looks great.
All right. Okay, so the benchmarks. This year we have 3 required benchmarks, right? So HPL, HPCG, and MLPerf inference benchmark. So these will be the required component of the benchmarks, right? And this will carry the highest weight for your benchmark submissions, right? And then we are also having a couple of optional benchmarks that you can work on. So these are stream and OSU micro benchmarks. So stream is for memory bandwidth and OSU is for your network performance. And these are pretty lightweight benchmarks, so you can finish them or run them pretty quickly within few minutes. So if you want to get a couple of bonus points, you can attempt to run those benchmarks and submit the results. All right, moving on. So the first benchmark, and probably the most important or the most popular one, is HPL, right? Before I go into each of the benchmarks, can I get a raise of hands, like how many people heard about these benchmarks, or are these all unfamiliar to you? How many of you know about these benchmarks already? Raise of hands. Anyone? Okay, so I see 2, 3. Okay. All right, so seems like most people are new or they are not finding the raise button. Anyway, so, okay. All right, so the HPL benchmark, uh, it's basically one of the most popular benchmarks is in the HPC world, right? And what HPL does, it solves a dense linear system of equations in double precision arithmetic, right? And these kind of matrix operations, the uh, finding out or solving equations, that's a very common uh, pattern or common subroutine that many scientific computing applications or scientific applications use for solving various things, right? So this HPL is basically indicative of the performance of a computer or a HPC cluster, right? And what HPL does is it generates a random matrix and then solves this dense linear system of equations and validates the output and then gives you some kind of performance matrix, right? And this performance matrix here is the number of floating point operations that it has calculated over the duration of the run, right? So number of floating point operations per second. And if you look at the top 500 list of all the supercomputers in the world, so they are basically using this HPL benchmark to show that, hey, my computer can do so many petaflops or exaflops of operations per second. Okay. And the top supercomputer in the world right now is uh, over 1 exaflops, right? And that is 10 to the power 18 operations per second. So with 3 computers or 4 computers, whatever hardware you have, you probably won't get to that level, but I'm pretty sure we'll have some interesting numbers from this competition that can be uh, that can come within the top few thousand of world supercomputers. Okay. Uh, so a little bit more details about HPL. So internally, HPL uses a lot of linear algebra libraries, right? So you can use different linear algebra libraries like math kernel library from Intel or OpenBLAS implementation or some other math library that you prefer. And then it also needs an MPI library for running across nodes, right? So if you are uh, running HPL on multiple nodes, which will be in this competition, you will need an MPI library to build HPL with. And then, as I mentioned, like HPL also verifies or validates the results from the computation. Uh, and then as you run HPL, so typically your problem size is determined by how much memory you have, right? Because the program allocates the array in your memory, right? And depending on how much RAM or how much memory you have on your machine, you can only run a problem of that size, right? So your uh, memory size is going to be uh, basically square of your array size, right? So it's n by n matrix. And from that, you can determine what size of the matrix you want to run this problem on. And then as you increase the size of the matrix, your runtime can also grow, right? So typically during your tuning phase or initially when you are practicing with HPL, it's pretty common to use a small matrix size. That way you can finish your runs quickly, you can tune various parameters, and then as you tune further and further, then you want to increase your array size larger and larger, right? But that will also take longer time. Uh, Building HPL, it's pretty simple. So you need the linear algebra libraries. So you will have to have some kind of BLAST library installed on your system, and you will need to point to those. You will need to point to your MPI installation, your MPI libraries. And once you have all of those dependencies, you can just run, configure, and make install, right? And HPL usually is pretty self-contained binary. So once you have built it, you can copy it somewhere and you can run the HPL binary. Now, the important part about HPL is the HPL input file, right? Because your run is controlled by this HPL input file, which is named hpl.dat. And the program will automatically look for this hpl.dat in the same directory where you are running it from, right? And what this hpl.dat file does is basically it specifies probably 10, 12 different configurations for running this HPL benchmark. And we don't need to modify all of those 10, 15 configurations. Mostly people play with these 3 or 4 things, right? So you will need to change the array size depending on how much memory you have across all of your nodes. The block size of computation. So this NB is basically the block size on which the algorithms in HPL are operating on, and that can make some difference in your performance. So you can try with different block sizes, see which one is giving you best HPL performance. And then P and Q are basically factorization of the matrix, and essentially your number of MPI ranks should match P times Q, right? And basically every MPI rank gets mapped to this P and Q factorizations. And to run HPL, you basically say MPI run or MPI exec or something like that, and you give it the number of MPI ranks and you point it to the HPL binary. And it will read this hpl.dat file, read all the configurations, and run the program. Okay. And as I was mentioning, so these are, of course, tuning guide for CPU-based processors. So I don't have tuning guides for GPUs or accelerators in this slide deck. So typically for CPU systems, the size of memory you want to occupy with your array is 80 to 90% of your total memory, right? And try different block sizes, see which one is giving you best performance. Your MPI process layout, and whether you are using pure MPI or you are using a hybrid kind of runs, with MPI and OpenMP, that can also impact your performance depending on your architecture and how your caches are laid out and so on. So the point is, do some experiment with your hardware ahead of time. See what kind of performance you get with different configurations, different parameters, and so on, and figure out the configurations that work for your cluster ahead of time. Okay. And here is a bunch of resources that I have come across for tuning HPL runs. Uh, these are for different kind of architectures, different processors. It may not match exactly with what processors you have for the competition. So you may need to look at Google and find out resources for that specific processor. Okay. Any questions so far on HPL?
I have a question, Amia.
Yeah.
So what about the NVIDIA pre-built benchmark? Do you know what I'm speaking of?
Yeah.
How do you feel about that? And, I know I have my opinion, but I'm just curious, are students allowed to use that pre-built benchmark?
Yes, so I think the rules of the competition is like, as long as it is open to the public, uh, we can use it. But the teams need to notify us that they are using these pre-built binaries, and we need to know ahead of time.
I would also say students should learn how to build HPL, because that will be, part of an interview, possibly. And so, don't just rely on the pre-built things. Learn how to build this yourself. So that's just some advice there. We have another question. Will we benchmark HPL with NVIDIA, AMD, Intel GPUs? So if you have those NVIDIA, AMD, or Intel GPUs, you should include them in your benchmark. I mean, again, Mia can stop me if I say anything.
No, you are fine. Yes.
Right.
Yes. The answer
And
is yes. Yeah.
yes, you should. I mean, because that will improve your score,
Right,
your
that will
HPL
improve
score.
your score. But remember, there are multiple components to your score. So we will also do interviews and report submission for the benchmark. So we'll grade you based on this overall, your overall performance across all of these.
Yes, but you definitely should benchmark with all your hardware, or at least the hardware that makes your machine fast, and those are going to be GPU.
As long as you are below the power draw limit.
Right. Of course. Yes. Yep. Good to mention that, Amelia. Thank you. All right.
Okay. Any other questions? All right. So let's move on. So the next one is HPCG, right? Now, HPL is in the HPC community. HPL is kind of a very nice benchmark, in the sense like you have array accesses and operations happening to contiguous array elements, right? So you can reuse a lot of your cached arrays and a lot of your cached elements, right? So HPL kind of gives you a upper limit on performance that you get on a piece of hardware, right? Typical HPC benchmarks, or not benchmarks, but typical HPC applications, they do not always have that nice of a memory access pattern as HPL has, right? So sometimes these applications would compute on sparse matrices. This would have random memory accesses. So you get a lot of cache misses once in a while. So the real life scientific applications, they would have performance uh, lower than what HPL indicates. So that's where this HPCG benchmark comes in. It's basically uh, doing matrix operations that have this kind of challenging patterns of execution, that have this random memory access, uh, that have a lot of communication. So that way, your computation is bound by these challenging factors, and you are not just computing your flop numbers, your floating point operation numbers, purely based on a compute bound operation. Right? And HPCG stands for high performance conjugate gradient. So it's basically using a precondition conjugate gradient algorithm for doing this kind of sparse matrix vector multiplication and various other linear algebra operations. And you can download this HPCG source code from the HPCG website. For building HPCG, uh, again, you need compiler and MPI libraries, uh, but HPCG does not have a hard requirement on a linear algebra subroutine. So you can just give it a compiler, if you give it a MPI library, and you can build it with those dependencies. You can also have both MPI and OpenMP support. So you can try different combinations running HPCG either with OpenMP, MPI hybrid mode, or pure MPI, see what kind of performances you get. Now, there are a couple of important things about HPCG. So one is, since it wants to evaluate benchmark performance when you have lots of cache misses, right? You want your array size to be large enough so that you get that kind of uh, cache misses and that kind of memory access patterns, right? So the recommendation is that you occupy 25% of your main memory or higher. If you use lower amount of memory, then maybe it will cache a large fraction of your uh, array inside the hardware cache, and that will not give you true performance for these kind of challenging matrix operations. And then the other important thing about HPCG is the benchmark must be run for at least 30 minutes for the results to be considered valid for submission. So make sure you run it for 30 minutes when you are running it during the competition, right? So you can run it for less time for tuning and for your internal practice and so on. But the actual submission must be 30 minutes or longer. Uh, and configuring and tuning HPCG. So I mentioned about the array size. So the array size in HPCG is a three-dimensional array. So if you increase one dimension, the X size, then Y and Z automatically gets expanded. So you get N cube sized array, right? Uh, Again, try different compilers, different MPI libraries. Sometimes that can give you different performance with HPCG. So see which combination works best. And when you submit your reports, we will ask you to include details of your builds, like what MPI library, what compiler did you choose, why did you choose that, and some justification along those lines. Okay. So try various combinations, see which one works. So one thing to remember is when you look at the HPCG results, you will see that this is orders of magnitude lower than the HPL results. Now, this does not mean that your hardware is bad, but this is how the benchmark is written and how it's supposed to work. So it kind of gives you some kind of a lower bound on your matrix operations for these kind of challenging sparse matrix operations. Okay. See a question.
Yes. So, question is, can we use vendor optimized HPL and HPCG, such as Intel versions? I don't know
Yeah,
about that.
yeah, I think the answer we said is yes. Uh, they need to be public, so we should be able to access those, and you should notify us ahead of time that you are using that uh, vendor optimized versions. But for your practice, as Jeanette mentioned earlier, that we will ask you about how did you build, how did you go about working with your benchmarks during the interviews. So we might ask you to show that you know how to build it from source, even if you don't use it in the actual competition. Does that make sense? All right. Uh, any other question on HPCG? All right. How am I doing on time?
About halfway through.
Oh,
If
wow.
you're going to spend an hour, yes.
Okay. Okay. Yeah, I think the next three will be a little quicker, so I don't have too much material. All right. So the third benchmark we have for the mandatory benchmarks we have is MLPerf inference, right? So MLPerf is basically a collection of benchmarks for various machine learning operations like object detection and classification and those kind of things, right? And this MLPerf inference is a benchmark that performs various inference operations on pre-trained machine learning models, right? And basically, you want to see how various hardware, various architectures perform on these pre-trained models with different data sets, right? And you use this ML Commons CM framework uh, to run these MLPerf benchmarks, right? And the CM automation framework, that's actually pretty nice in that it can automatically uh, configure your runs. It can use the compilers that you specify. It will automatically download the data sets from the internet and so on and so forth, right? Uh, so if you have never played with MLPerf, uh, please go ahead and play with the CM command line, CM options, see how you can run this MLPerf inference benchmarks. And I will refer you to last year's SCC22 instructions on MLPerf. And last year we did object detection with the RetinaNet model with OpenAI, OpenImages datasets, right? And you can get started with MLPerf from that instructions or from that tutorial that was posted last year. And I will give you a link to the GitHub page of that as well. Okay. And as we finalize the submission instructions for the benchmark, we'll give you more instructions on what will be the actual size of the validation data set we want to use, what will be the different pre-trained models we'll be using, and so on. So this year we will be doing a little bit more expanded version of last year's component MLPerf inference run. So this year it will probably include multiple pre-trained models for your inference runs. Okay, and uh, we'll give you detailed instructions on those as we finalize the exact models to use. And as I was mentioning, so use this tutorial that was prepared for SCC22, and they had a very nice step-by-step instructions for how you can download the MLPerf CM framework, how you can download the datasets, how you can run the inference benchmarks with various compilers, and even for GPUs and so on. All right. Any question? All right. So these three are all the required components of the benchmark. Now, moving to the optional components, we have two benchmarks, Stream and OSU micro benchmarks. And Stream is for measuring the memory bandwidth, the sustained memory bandwidth achieved from your computer, right? So how much data can I read from your main memory to the processor at a sustained rate? Why is this important? So a lot of the scientific applications, a lot of the linear algebra kernels, they operate on very large data sets, right? Very large matrices and so on. So you cannot fit all of that into your cache or into your registers and so on, right? So you have to read from main memory and you go back and forth. So the performance of a lot of these linear algebra operations are constrained by how much memory bandwidth you get on your system, right? So one example would be why GPUs have such high memory bandwidth, right? It has, let's say, thousands of cores. Now, in order to keep these thousands of cores busy, you need to read a lot of array elements into your caches and into your registers very, very fast, right? So in order to keep the compute elements or processors busy, you need fast memory access. And Stream benchmark is measuring that, right? So you can run Stream on your machine. You can run it either as single core or multiple cores. Stream is a single node benchmark, right? So you don't have to run Stream on every node of your cluster at the same time. You can run it on one single node, right? But in order to get the maximum memory bandwidth, you need to run it with multiple cores. Now, the definition of multiple cores can vary depending on like how many cores can saturate your memory bandwidth, right? So if you have 128 core, maybe running on 16 cores will give you the best memory bandwidth performance. And you need to figure out from experiments what is that magic number that's giving you the best memory bandwidth on your hardware. Now, important thing for running Stream is you want your array size to be larger than your L3 cache. So your array size should be at least twice the size of your L3 cache on your system, or all the L3 caches combined if your hardware is designed that way. Because otherwise, all of your array elements will be in cache, and it will not be a true indicator of your memory bandwidth. Right. Now, when you are running streams, the binding of your cores to physical threads, or binding of your OpenMP threads to the real cores, the physical cores on the system, can have varying in performance. So try it with different layout of your OpenMP cores, OpenMP threads on your system, and see which one is giving you better performance. And try it with different compilers. I have noticed like Intel and GCC, they can give very different performance numbers with stream. So identify which one gives you the best performance with what compilation options. And yeah, and again, running stream is pretty straightforward. You just set the number of threads you want to run it on. You specify OFB num threads, and you just execute the binary. There is no MPI in it, so it's just a single node execution. Now, if you have heterogeneous hardware amongst your compute nodes, right? So we are only considering benchmark numbers from your compute nodes. If you have compute nodes with different kinds of hardware, we only want the results, the best result among those hardware, right? So if you have three different machines with three different memory bandwidth, choose the one that has the best memory bandwidth and submit the results from that, and definitely indicate what you have done, that your theoretical bandwidth for different hardware that you have are XYZ, and you pick X for running stream, and here is the actual output. All right. Jeanette, did I capture that correctly?
I think so. Yes.
Okay. Any question?
Yeah. So Mary, somebody asked the question: will the stream benchmark info be posted on the website? And I do have so the stream and the OSU micro benchmarks information, which we will get on the website shortly.
All right. Okay. And here are the stream resources. So this is the original website to download the stream benchmark, the virginia.edu, and then there's a nice tutorial from Intel on how to optimize runs on Intel systems. If you have different hardware, then you can look for other vendor recommendations on how to run it on their systems. All right, the final benchmark piece is OSU micro benchmarks. And what OSU micro benchmarks do is basically measure the performance of various MPI operations. And it's primarily dominated by the question like, how good is your network, right? So if you are whether you are using Ethernet or whether you are using InfiniBand, your performance of various MPI operations will be determined by these network setup that you have, right? And also sometimes your MPI library or implementation of your MPI library can also determine the performance that you get, right? So the OSU benchmarks, the micro benchmarks will determine how good is your network, how good is your MPI library. And both Stream and OSU, you can think of these two benchmarks as kind of a sanity check against your cluster setup. So that's why we have these two as optional benchmarks, because you will need those to validate your cluster, make sure your network is optimally set up and it's performing fine, make sure your uh, processes, your computers are correctly set up and you are getting the desired memory bandwidth from Stream. Those are, both of these are kind of validation for your cluster, right? Now, in OSU micro benchmarks, uh, they have a lot of benchmarks for every single MPI operation uh, that's there in the MPI standard, right? Now, there are three primary kinds of benchmarks. One is called point-to-point, meaning you have two nodes and you are doing MPI communication from one node to the other. Uh, the other one would be collective operations, where you are doing some kind of all-to-all communication, right? Or many-to-many communication. And then the third one is MPI one-sided operations. Now, we don't need to worry about all of these. We are only looking at the latency and bandwidth to keep things simple, right? So we want to measure the MPI latency uh, between two nodes in your cluster. Uh, Same thing for bandwidth. We want to get the maximum network bandwidth uh, between two nodes on your cluster, right? So work on these two point-to-point OSU micro benchmarks. These are called OSU latency and OSU underscore BW or bandwidth. Uh, Again, you can download it from the MLPerf website. So it's published by the Ohio State researchers, and it needs your compiler and MPI libraries. Once you have those dependencies set up on your system, you can just do configure and make, and then you can copy the binaries or make sure you add the path to the binaries to your system environment, and then you run the binaries with MPI, right? One thing to be careful, and I have noticed people often make mistakes, is make sure your MPI ranks are actually distributed across both nodes, right? Uh, Sometimes when you work with a scheduler and you allocate lots of cores, it will just launch your MPI processes in sequence, right? So it might launch everything on one node, but that's not a true indicator of your uh, OSU latency or OSU bandwidth performance. We want to measure the latency or bandwidth across two nodes on your cluster. So make sure your two MPI ranks are on different nodes. Uh, the other important point to consider is if you have heterogeneous compute nodes, uh, try to identify two compute nodes that have either identical or the closest specs, right? So we don't want uh, one one node with, let's say, 128 cores and other node with 32 cores and do a lot of strange MPI placement and not have a good run. So try to keep the two nodes identical so you have these kind of noises or variations to a minimum. And then submit the benchmark results across these two nodes. All right, so that's all I have on OSU benchmark runs. Any question on the OSU runs? Okay, either I have managed to confuse everybody or people are just shy. Yeah, if you are doing benchmarking for the first time, I understand this is a lot of information. Take it slowly. So I would recommend that start with the easiest benchmark. So let's say stream is the easiest benchmark. It's a single C file, C or Fortran file. You can just compile it with one command. So start with the simplest case. See if you can run it. If you can compile it, run it, move on to the harder benchmarks after that, right? So stream, OSU, these would be fairly low overhead to compile and run. So start practicing with those, and then you can practice with HPL and HPCG and MLPerf. Okay, and for MLPerf, remember that MLPerf is more Python based, so you will need to familiarize yourselves with how to create Python virtual environments, right? How to install your own Python and install MLPerf with that particular Python, right? So MLPerf is a little different than other benchmarks that we have on the list. So in order to run MLPerf, you will have to consider those Python related subtleties. Now, notes about benchmarking. We will release detailed submission instructions later, and as we get closer to the competition, I'm pretty sure at least a month, Jeanette. So probably a month from the competition, uh, we will give you final instructions on how to submit, how to name your output files, what to submit, uh, and all the details. Okay. Follow the submission instructions very carefully, because as you can see, like there are lots of components to the submissions. Uh, Familiarize yourself with the benchmarks ahead of time. So get started right now if you have not already, right? Uh, Write scripts and automate as much as you can, like building all of these benchmarks. That should be uh, automated as much as possible so that you spend least amount of time building that when you are building your cluster during the competition, right? Write your scripts to run these benchmarks. That will help tremendously, right? Even if it's running on a single node or on three nodes, uh, write scripts that will speed up how fast you can iterate on various benchmarks, how fast you can tune on various parameters, and so on. And then if you want to use some kind of build framework like SPAC or EasyBuild, you are welcome to do that. SPAC uh, has recipes for building HPL, HPCG, Stream, and OSU. So that should be fairly easy and straightforward. But you will have to remember to set appropriate flags for OpenMP or MPI, or what kind of libraries you want to use, what dependencies you want to use, and so on. So that's there's a little bit of learning curve involved there. But if you are familiar with SPAC, that can help you tremendously with software or benchmark builds.
So there's a question.
Yeah.
Will we still be running all benchmarks during the Monday benchmarking time? So yes, on Monday, we'll start about 8 in the morning again. There'll be a more specific schedule later, and you'll have till about 5 p.m. to run your benchmarks. I would say for the stream and the OSU micro benchmarks, those you wouldn't need to run on Monday. Those aren't, there's no power limit to them or anything like that. So those are different kinds of benchmarks. Just, run them on your cluster. You can do that ahead of time. Be prepared to explain that you understand those. Your team should be able to understand those and then explain that to the judge, and then and report some results. But for the 3 main benchmarks, those have to be run on Monday, and they have to be run under the power limit. And so there's a certification process that happens where you will start your benchmark, run it, and then once you're done with it, you'll report that you've run that benchmark. And we'll explain that and have details later on how to report that, but you'll do it in real time that you just ran it. And then we will check your power and look at the graphs and make sure that you didn't run over power during any point of the benchmark. So those have to be certified and run during that Monday period. Did that answer your question? Yes. Great. Thank you.
All right. So yeah, I think that's all the slides I have. Any other questions? And if you have any other questions that come up later or want clarification on something, please post on Discord. So I'll watch Discord for any questions and we can answer there as well.
And AMIA does mean discourse.
Oh, discourse.
I just don't want to confuse people with the Discord.
Sorry.
There's not Discord, but discourse. We have the discourse server, so you all know that. But yeah, AMIA's on there, and so feel free to ask some questions there.
Many similar names.
I know it. All right, I think that's about it. Thank you, AMIA. That was great, and we will see everybody next time.
All right, thank you, everyone. Good luck.